There are many cases in the real world, especially in mathematical and scientific areas, where we encounter very large or very small numbers. Scientific notation, also known as standard form, provides a universally recognized, succinct way to represent such values. A number is in scientific notation when written as a number from 1 up to, but not including 10, multiplied by a power of 10. Importantly, any decimal number can be written in this form, although its true advantage is to replace very large or very small numbers with this more succinct notation. Rounding is often required, as we will see later. It is important to be able to interchange between decimal form and standard form, which is scientific notation, especially in mathematical, scientific, and engineering fields. A convenient technique is color-coded in these last two examples. For numbers greater than 10, we write the non-zero digits out the front, although we might need to round or include extra zeros to indicate the correct level of accuracy. We place a decimal point after the first non-zero digit here. Then we count the number of digits between the new position of the decimal point and its original position, here, on the end of the number in this case. We find the decimal point has moved 24 places. This tells us the power of 10 required. It's a positive power because we need to move the decimal point to the right to put it back where it was. In other words, 9.23 is multiplied by 10 24 times to create the large number we started with. For the second example, we have a very small number. The original position of the decimal point was here, but now it's here. Counting the digits, we find that it has moved 16 places. We would need to move it 16 places left to put it back where it was. So the power of 10 is negative 16. You might like to pause the video and try these two yourself. You should immediately realize that the first number is more than 10, so its power of 10 will be positive, whereas the second one is less than 1, it's a decimal, so its power will be negative. Now we just need to figure out the values of the powers by counting the digits between the original position of the decimal point and its new position, which is always after the first digit that isn't a 0. Here, 17 digits this time, so our number, written in scientific notation, is 7.8401 multiplied by 10 to the power of 17. For our small number, we place the decimal point here after the 1. There are 10 digits in between, so the power is negative 10, giving us 1.050 multiplied by 10 to the power of negative 10. Notice that I kept the extra 0 from the end of the decimal. Extra zeros on the end of a decimal are clearly showing you more information about how precise the value is. We might elect to keep extra zeros for the large number case as well, if we also want to show more precision. To fully appreciate why and how we determine the number of digits to keep, you need to understand significant figures, which I discuss in this video of the same name. In summary though, the number of digits you keep out the front here must match the number of significant figures you require. We won't focus too much on this in this video. Now we can summarize the simple steps to follow for changing any number into scientific notation form. I will complete these two examples as we go. First, we move the decimal point to follow the first non-zero digit. This always gives us a value greater than or equal to 1, but less than 10. In our examples, we get 7.39 in both cases. Then we count up the number of places we have moved the decimal point. The easy way to do this is to count the number of digits between its original position and its new position. Counting the digits between these two positions tells us the power of 10. In both our examples, we have moved 8 places, to the left in the first one and to the right in the second. To determine the sign of the power, simply look at the original number. If it was greater than 10, the power is positive. If it was less than 1, the power is negative. There is one case our summary doesn't cover, when the number is less than 10 but not less than 1. For example, 7.39. In cases like this, the decimal point is already after the first non-zero digit, meaning it does not have to move any places at all. Writing it in scientific notation means the power of 10 is 0, like this. Of course, there is no benefit in doing this. Remember, scientific notation is intended for very large or very small numbers. By the way, 10 to the power of 0 is equal to 1. So we really have just multiplied 7.39 by 1. Let's practice with some more examples. Pause the video if you'd like to try them on your own first. Number 1 is hopefully obvious because we see 7 zeros after the 2, meaning it is 2 multiplied by 10 to the power of 7. If it wasn't obvious, then following the steps we would move the decimal point from the end of the number to follow after the 2. Then, counting the digits between these two positions gives us 7 for our power of 10. Remember, we could also write 2.0 or 2.00, etc. if we needed to show that the value is more precise. In number 2, we move the decimal point from here to here, telling us the power of 10 is 5. So our answer is 3.74 multiplied by 10 to the power of 5. I won't keep adding zeros for every example, just keep it in mind when greater precision is required. In example 3, we move the decimal point from here to here 11 places, giving this answer. In this example, our answer might be too precise, and we could round to something more suitable, such as 2.5 times 10 to the power of 11. Next, after moving the decimal point, we count only 3 places, resulting in 8.3516 multiplied by 10 to the power of 3. For number 5, 90 is only 9 lots of 10, which means 10 to the power of 1. There is no real benefit in writing 90 in scientific notation. The rest of our examples are all numbers less than 1, so we immediately know all their powers will be negative. For number 6, we move the decimal point to be after the 5, a total of 4 places, so the power must be negative 4. We have 5.1 times 10 to the negative 4. Next, we have only one place to move the decimal point, so 0.3 is the same as 3 times 10 to the power of negative 1. And in the last one, we need to move 10 places to jump over the 9, so the power is negative 10, giving us 9.504 times 10 to the minus 10. Now let's see how we can change numbers presented in scientific notation back into decimal form. Naturally, we need to do the process in reverse, putting the zeros back in place as we go. For positive powers of 10, as we saw earlier in the video, the power tells us how many places right to move the decimal point, and negative powers mean move it left. In both cases, if we run out of digits to jump, we fill in with zeros. Pause again if you'd like to try these examples on your own. In the first, we need to move 5 places right. After jumping the 0 and the 1, we need 3 more, so we fill in with 3 zeros, giving us 301,000. In number 2, the decimal point isn't shown, which means it's at the end of the whole number. We need to jump 9 places to the right, so we simply add 9 zeros. In the third example, we need to jump 2 digits. There are 3 available, so our decimal point ends up after the 7. We should still show the last 0 because it provides extra information about how precise this value is. The final 3 examples all have negative powers, so the decimal point will move to the left. For negative powers, you will always fill zeros after jumping the first digit, since there will always be only one digit in front of the decimal point when written in scientific notation. This provides a convenient shortcut, ignoring the negative, The power tells us how many zeros to write in front, and then we simply place a decimal point after the first zero. In example 4, we need to move the decimal point 5 places left, so we write 5 leading zeros and place the decimal point after the first one. Next, we only need to move 1 decimal place, so we jump the 8. We still like to place 1 zero out front. In the last one, we write 11 zeros in front of the 9, 10 of which will be after the decimal point. This example illustrates why scientific notation is so useful. It's often so much shorter to write. Imagine if there were 20 or even 30 zeros after the decimal point. To see how to use scientific notation on a calculator, I recommend you watch this video or the in-depth version of this video.